Okay. So the first one should be easy, right? Because you actually did that. You're supposed to have done that for the midterm, sorry, the exam, right? So what's the answer? Do you do that for process switch? Do you have to flush the TLBs for process switch? Sorry? Yes? What about kernel context switch, kernel thread context switch? The answer is no, right? Because both the threads are part of the same address space. Both the threads are operating on the shared data, right? So whatever TLB translations you did for one thread is still valid for another thread, right? So you don't need to flush it. The last one, user level threads. Again, the answer is no, because if it's not true for kernel level threads, it's not true for user level threads too. But the thing to remember is, in the user level thread, when you do a context switch, the kernel need not get involved, right? The user level thread, the definition is it's done by a library. The operating system does not even get involved. So you have to be careful to say operating system can do anything at that point, because it's not getting involved, right? If you do the user level thread library good, then the context switch is done entirely by the application. The operating system does not get involved. So if it does not get involved, it cannot do stuff like flush TLBs or what have you, right? So the answer is false, but it's a little bit more tricky than that, because if it's a application level stuff, the operating system does not get involved, right? So for the copy and write, what's the answer? We talked about copy and write in class as a technique to solve fork issues, right? So when you fork a process, you get another copy, and this is a way to optimize creating the new copy. You wait till somebody tries to modify it, right? And no such semantic exists for threads. So when you do a thread fork, you have the same, they all operate on the same shared data, so you don't need anything like copy and write. Right? How many of you got that right? Okay, a few. So for the folks who said it's true, why did you think it was true? The answer could be you forgot what copy and write was, which is okay. I mean, which means that you need to go look it up. But is there another reason why you thought this was true? Yeah, if you have any confusions about these, let me know, right? Sorry. So the homework project 3 should be here, right? And some of you asked, are you supposed to experience Bellardi's anomaly or any of those issues, right? And the answer is you may not really feel it, because a real program goes through a number of different phases, right? It goes through, so how many of you actually looked at the memory traces to see how widely your program goes through the stuff, right? It accesses lots of pages, it accesses lots of addresses, right? So it does not behave in a certain nice fashion that I can say in the class, right? It does not go through a little loop. It goes to some initialization, it accesses lots of libraries, and then it does something, right? So it's very hard to see simple behavior in real programs, because real programs have complex, they jump around, right? So you may not precisely notice the things we talk about, but that's what real programs do. Real programs jump around, right? And we'll see how that affects what we do in a little bit. But essentially, real programs go through different loops, different initialization. So initialization code tends to be straight line, and then it may go through some loop, then it goes through a straight line code, then it may jump around, and that's the nature of real programs. And since you use the pin tool analyzes a real program, And so the nice thing is you get the behavior of real programs. And the nice thing is you can kind of see that it's not very easy to come up with one policy because it's very hard to understand what the program is doing, right? So where we left off in the last class was the notion of an optimal algorithm, right? An optimal algorithm cannot be built because essentially you need to know what the reference string would be for the future, right? So you could build an optimal algorithm for your case because you got the pin trace. So you can look at the pin trace to see what pages will be accessed in the future and hopefully come up with a different algorithm which will keep the right set of pages that you would want in the future, right? But in a real system, you can't do that because you can't look at the future. So you, at best, you can look at the past, right? But you can't look at the future. So you can't know what is the page which will be used furthest into the future. And if you replace that, you expect to get the least amount of page faults. But since you can't know the future, you can never achieve the optimal performance. But it's a good way to kind of see how close you are, right? So one thing you could do for your homework project is if you ran an optimal algorithm where you looked into the future of the references and replaced the ones which will be used the furthest into the future, then you get a sense of how much page fault you should get for a particular scenario, for a particular number of page frames, and see how close you are to that optimal. Even though you can never achieve it, you can kind of see whether you're really far, whether you need to do something, how you're close, right? So this is a way to analyze a system rather than just blindly figuring out how the system should behave, right? So some of the other algorithms, one of the closest way to make your application look similar to a optimal algorithm is the least recently used, right? So the idea here is I would like to replace the one which will be used further into the future. Since I don't know the future, I'm going to look at the past to see which one was used further in the past. And I'm going to maintain that whatever was used further in the past is likely to be used further into the future, right? That's the intuition we decide for least recently used. So we want to know which will be used furthest into the future. We don't know what that is. So we figure that since we don't know what will be used furthest in the future, we're going to look at what we accessed in the past, which we already know. So if you look at what was accessed furthest in the past, then it's likely that it will also be used furthest into the future. Do you buy that? Does it always have to be true? Or can you think of cases where this is not true? Yes?
You could have just got done accessing some block of memory and not going to need anything. But
Yeah.
just one of the most recently used program.
Yeah, so depending on the program code, right? Sometimes you might have finished using one segment, you go to another segment, right? But this is considered to be a sort of a reasonable assumption, right? And as you can imagine, there are cases where this will be horribly wrong, right? Just because you use something in the way past may mean that you're just going to start using it again, and that won't be captured here. But it's a reasonable assumption, reasonable. It might work for some cases, so we'll have to do that, right? So we can try to do that, right? So to implement this policy, right, taking of your data structures from some 200 level class, how would you implement least recently used in a system? I have a bunch of references that are being made to certain pages. How would I figure out what is the least recently used? In this case, we have the reference string as 1, 2, 3, the one up there, right? And we have a certain way of going through this stuff. Let's make it simpler. Suppose I'm making references like this, and suppose I have 3 slots, right? So first I reference 1, then I reference 2, then I reference 3, then I reference 5, right? So at this point, how do I know which one was the least recently used? So my current time is here, right? Which was recently used? 1, right? So how would you implement this stuff? How would you do this? So you have to keep track of this, right? So you have to keep track of when you're accessing something, right? So you'll have to keep track of something here which tells you what time it was accessed, right? So one way to do that is to add time, right? Let's say this time here is 1, it keeps moving like this, right? So what we can do is, when I access this page, I mark the time that I accessed it, the time that I accessed it, the time that I accessed it. So when I have to find the least recently used, I go through these times to figure out the least recently used, right? So I need to search through these things to find the smallest number, right? So I have to search through these numbers and find that 1 is the smallest, so this is the least recently used, right? So if I move forward 1, and let's say I replace this with 5, right? So at that time I have to make this 4, right? At time 4, I replace this, and the time this was accessed was 4, right? So when I come here, which is the least recently used? 2, right? And the way I find that is, now I go through this search, I search through these numbers, and I find this is the least recently used, and I replace this. So I put 6 here, and I put 5 here. Does that make sense? Right? So to implement this, I need 2 things. I need to keep track of when a page was accessed, and I need to have a way of searching through these things to find the smallest number, right? So even though conceptually it's simple, even though conceptually you can look at this and go like, yeah, I mean, it's obvious 3 is the smallest number. Think of your example 1, right? You had 408 frames, right? So somebody has to keep track of all this stuff, and somebody has to search through all this stuff to find out what the least recently used is, right? So who can keep track of this? Can the operating system keep track of this, or do you need the hardware to keep track of this? Is it done? Does it need to be done by the MMU, or can it be done by the operating system? Going back to how things are done, right? You set up the page table in a simple case, right? And when the page table is fine, when the entries are valid, right? So for example, all these values will be valid, right? Your program runs, right? The operating system does not get involved. So your program, whenever it finds this is valid, you can access this memory, and everything will be fine, right? So this has to be maintained by the hardware, not by the operating system. Because if things work fine, if the entries are valid, operating system does not get involved when you try to do the access, right? It only gets involved if some page was invalid, or you're trying to find some new page. So that means this has to be done by the hardware. So you need some hardware support to keep track of these counts. You need some hardware support to do this search, right? And that's a pretty very hard problem, right? So you can't force the hardware to say, now you have to keep track of all these large numbers. Now you have to search through this large number of numbers to find the smallest number, right? And so many hardware cannot fully implement this notion of arbitrarily large number, arbitrarily large clocks, because now for every page table entry, you need to have a large counter. It has to be updated every time you access this page. It has to be searched every time you need something, right? So we do shortcuts to implement sort of what you want, right? So you can't implement the true least recently used, because true least recently used means that you need to keep track of all these things precisely. You need to be able to search through all of them precisely. And since hardware cannot be expected to search through a large number of numbers in arbitrary fashion to find the least recently used, you approximate it to find sort of least recently used, right? So for example, one way you can do that is the hardware can say that if you access something, I will leave you 1 bit, right? So if you access some page within certain times, I'll mark it as 1. So the hardware can guarantee you that if you access something, then it can modify it as 1, right? So operating system can play tricks with that facility to achieve a true counter. The way it does that is every clock cycle, right, every 1/100th of a second or so, the operating system will go and mark everything as zeros, right? And it'll let it run, let the program run, right? So the next clock cycle, what it's going to do is, it's going to see, so if you access this page and this page during the last interval, the hardware would have made this into 1 and 1, right? So you go back and you look at how many of them were made 1, how many of them were made zeros. So if this ones are made 1, then if this was 0, then you know that, so let's say you take time, right? Every so often, at this point, you go and look at how many of them are 1s. So you know this is 1, and this is 0, right? Which means that within this interval, nobody accessed this one, right? And then again you do 0, 0, 0. And at this point, let's say you notice that this one was not, this is 1, and this is not, right? Then you know that within from here to here, right? This was accessed at here and here. This was accessed here. This was not accessed in any of those, right? So that way, an approximation of LRU would be, this page was not accessed within the last 2 epochs. This was accessed 1 epoch back, and this was accessed all the time. Did that make sense? One way to approximate LRU by using these reference bits is, if the hardware only gives you a facility that if a page was accessed, you'll change something to 1, right? So every time I keep changing this to 0, if the page was accessed, then this bit would have been set to 1. So every so often I go and see if the page has been set to 1. If it has been set to 1, then I know that in the last some time this was accessed. So this is not likely the least recently used, right? So I have to look for the ones which are not accessed. So I keep track of this in software. So this is a hardware-software partnership. So hardware tells you this is set, and the software keeps track of this. So we can use this to approximate LRU. Can we? So what's the problem with this approach? How bad is it from a true LRU? Yes?
We'll only be able to look at the most recently used within that time period, so it won't be probably deemed least recently used, it'll just be one of the least recently used.
Yeah, so it depends on how often you do this stuff, right? It depends on how often you do this stuff, and it does not also care how many times you access stuff, right? So you would want to make this smaller and smaller, so to get a finer sense of how much this happens, right? If you keep this too long, then let's say if you keep this for an hour, so that basically means that within the last hour, something was accessed. It might have been accessed once, it might have been accessed a million times, you don't know, right? So you want to make this small as possible. So what's the cost of making this smaller and smaller? Do you want this to be small or large? You want this to be small, right? If you keep it too large, then you get very coarse notion, right? So in the worst case, let's say if you have hour, that means the page was accessed within the last hour, which doesn't really say much because probably most of the pages were accessed at least once an hour, so you're not going to get much, right? So you want to make it as small as possible. But what's preventing you from making it really small? Can you make this every instruction? That's practically the smallest you can go, right? Can we? Why not? So if you make it smaller and smaller, let's say you make this 1 nanosecond, right, which is a very small number, right? Which means that what happens is every 1 nanosecond, your operating system has to go through every process. For every process, it has to figure out what all the pages are. It has to go and look at the page table entry for each of those pages. It has to add, so it has to keep another table here, right, which keeps track of all the stuff. So it has to say, okay, in the last 1 nanosecond, I noticed this modified, this modified, this modified. It keeps track of all the stuff. And then it has to go and make everything into zeros and lets it go, right? So if you do it at every 1 nanosecond, you have to do all this work to keep track of doing this, right? It's all being done by software. Hardware only sets these bits. So you let one instruction go. Now you have to go through all the pages to see which ones got flipped, and you have to keep track of all those, and then you have to reset those, right? So you don't want it to be so small, because essentially what will happen is all you're doing is setting this. I mean, the operating system is now spending all its time doing this table, right? So you want to set a balance where you're not spending all your time doing this, or so you can't have it too accurate, because if you do it too accurate, then you spend all the time basically keeping track of this data. So you want it at some nice time interval, right? Which means that it's not going to be true LRU. It's not going to replace the most recently used. It's not going. It's going to be pseudo LRU kind of stuff, and that may be okay, right? And that may be okay because that's a reasonable approximation, because that reduces the amount of overhead. It's what the hardware supports, and you kind of go along, right? So that's some of the problems that you face when you do a LRU kind of stuff compared to what you do in your algorithm. In your algorithm, you can run a real LRU. You can do sorting. You can keep track of any data structure and what have you. But in a real machine, this has to be done with the partnership between the hardware and the software. And there's only so much you can do, right? So that's what we're going to look at in this next few slides. So that's essentially what happens. If you look at the reference bit, we can draw it on the board to figure out which was the least recently used. But when you try to implement it, you can't implement the real thing, because to do that, you need to keep track of the absolute time, and you need to keep track of, to be able to search through all the accesses, right? Keeping track of the real time would mean that you need to have enough memory in the page table. And searching through all of those pages is not a trivial task, especially since this has to be done by the hardware. So you don't want to do that. So there are a number of different ways of implementing these, right? So one way is you can actually have the operating system maintain the counter, where every time you'll copy the clock, right? Every time you access a page, you'll copy the clock into this shared and have a entry in the page table, right? Then you can implement the search either in your operating system or in the hardware to figure out which page should be replaced. And even though you would like this, very few hardware will let you, there's too much overhead to keep track of the time, copy the time into the memory page and all those things. It pollutes a whole bunch of caches and stuff. So you rarely implement this functionality. Another way to implement this is through a stack implementation, right? Where so you want to avoid this search problem. So you try to keep a stack of all the pages, and you use the stack to figure out which is the least recently used, because at the end of the stack is the one which is least recently used. So for example here, so if that is a reference string, right? So if you had a stack like this before, right? Which means that if you are at the point A, 2 was the most recently used, and then the 1. So you have 2, 1, 0, 7, 4, so on. So when you next access 7, right? You basically move 7 to the top of the stack. That is the most recently used, and 4 is the most least recently used, right? So essentially, you keep track of the structure all the time. So when you want to replace, you basically go and find the last entry that's least recently used. The challenge is you have to maintain these pointers after every access, right? So if the hardware supports it, it's good. Otherwise, the overhead is really a lot. You need to change 6 pointers, like what the book pointed out, to make sure that after every page access, you keep this sorted in the stack order, right? The other cases are the ones that I just talked about. It's the notion of a reference bit, right? So reference bit, basically the hardware says that one bit will be flipped every time a page is modified. So as operating system, you have to periodically go in, right? Set the bits to be 0, and then see when it turns to 1. When it turns to 1, you get a sense that page was accessed. You don't know how many times it was accessed. You don't know when it was accessed within the interval, right? But you know it was accessed. So this gives you a coarse understanding of what the least recently used bit is, right? And for the most part, that's a reasonable one. And some operating systems some hardware is a little bit more powerful. Rather than giving you 1 bit, it may give you multiple bits, right? So it may give you 2 bits or 3 bits or 4 bits. And they also give you a way to figure out if the bit is an overflow, right? Because if let's say there's a 3-bit, and eventually after 8 accesses, it will become to 0. So it may also have an overflow bit. So you can use that to see it was accessed a lot. So you can use that to kind of get a sense of which page among these things was accessed, right? So depending on what the hardware can give you, you can play these tricks to kind of learn how these things happen, right? The key thing to remember here is operating system is not involved in every instruction. So once it gives control to the hardware has to do whatever, and then you're trying to go and figure out what really happened. You're basically trying to figure out, okay, maybe, after I gave control back to the hardware, when I came back, the bit was set, so that means it was accessed somehow, right? I don't know precisely when it was accessed, but sometime in the last epoch, so I'm going to be good with that, right? So another algorithm is the second chance algorithm, which tries to give you one more chance. So it basically sets some field to replace the page, and the first time it has to replace it, it gives it another chance, right? The hope is if it was used again, then it can be left alone, right? So why would people try all these different kinds of stuff? Why would it try second chance and all those things, right? Is there a science behind what replacement policy you should use on a machine? Can you think of a good policy other than the optimal policy which cannot be implemented, right? Optimal policy has to look into the future, right? You're done for the homework project, right? Which policy did you think would be good? Which policy was good for you for the homework, the first trace? Which policy did you guys find was good? Sorry? Least recently used. Was it good for all the 3 cases? The page policy was good. Was the second chance algorithm good for under any circumstances?
On ours, it was pretty close to at least used for a couple of
Yeah, so one of the things you find is, like, if you're Microsoft, you're practically simulating these things all the time, right? You guys looked at a very small trace, but if you look at a really large trace, if you look at, say, PowerPoint, right, you couldn't really run it. So one of you actually, I think, tried to monitor a big program. So you created like a 30 gig trace file, right, and it overflew the file system size. You'll find that very quickly you'll create tons of traces, right? So if you run it on like, say, Emacs or one of those programs, you'll get lots of traces, right? So you want to keep analyzing them. You want to try to figure out what happens, right? So you'll find that in real programs, not the toy programs we kind of looked at, the behavior is so complex that in some cases, the second chance actually does help, right? So you're trying to tweak, you're trying to find, there's really no science here. You're trying to see how programmers write the program, how the traces are happening, and you're trying to see what might help you with this stuff, right? So under some circumstances, the second chance may actually work out for you, right? And so they're constantly trying these things. So when you come up with a new version of operating system, they're trying to tweak these things because things keep changing. Things keep changing because you have different programs, your programs take a lot more data, and you have a lot more memory. So those things plus the hardware. So this is one of the things where it's continuously actively investigated. Some of these policies look like heuristics, but they're based on observations. They're based on observations where people see, okay, this is what people have been writing programs, and this program could have been helped if you have a second chance, what have you, right? So the idea of second chance here is, if you want to replace that, if you're using a clock algorithm, you want to replace that as the next page, rather than replacing it, you make it 0 and go through it again, right? So you want to replace that, you change it to 0. You want to replace the next one, so you go to the next one, it was 1. So give it a 0, and then you find something which is 0, right? The notion here is, if the page was accessed before you come back, the hardware would have set it back to 1, right? Which means that it was accessed within the last one epoch, right? So I set this page to 0, and I'm trying to look at them in the sequential order to replace them. If you access the page, your hardware would flip that 0 bit back to 1, which means that you get one more chance, right? So I mark you to be deleted, and I give you one more chance within the next cycle to see if you will be accessed. If you're accessed, you live. If you're not accessed, you're replaced, right? So this gives you a little bit more chance. So if a page was suddenly begin to be popular, then he'll come back into the use, even though it was least recently used, right? There are also other variants, right? The other variants are, rather than looking at when it was used in the past, keep a count, right? So if a page is used a lot, then maybe that should be kept, right? So rather than keeping a track of whether it was accessed or not, keep a count of how many times it was accessed. So you can replace either as least frequently used or most frequently used, right? So I can kind of look at how many times the page was accessed, and the page which was accessed the least amount can be replaced. That would be the LFU. And most frequently would be the one where the one which is most popular would be replaced, right? So what is the problem when you think of least frequently used? If you're trying to replace a page which was used the least amount, what are the one things that can go wrong? Yes?
Something could get used a lot and then never used again, but it will never get replaced if nothing ends up.
Yeah, so your historical usage pattern always helps you, right? Think of this as a student kind of stuff, right? So if you only give students who got the best grades from kindergarten the more best grades, right? Then you're kind of stuck. You can never improve upon because you're kind of living in the past, right? So you don't want to keep the past all the way. So you have to somehow age the past, right? What's the other problem with using least frequently used? I keep track of how many times a page was accessed. I replace the one which has been used the least amount of time. Yes?
You might be replacing, like if you just loaded a page,
yeah.
You haven't accessed it that much, but you might be accessing it in the future. So.
Yeah. So you never get enough accesses to stick around, right? When you're brought in, right, you're the first one to go because you just were brought in. So unless you start accessing the page a lot, you will be thrown out immediately, right? So depending on how your program proceeds, if your program comes into a new phase where it's trying to access a new set of pages and it brings the page, immediately it gets thrown out, right? So you are going to retain the one which is in the past, And the new ones can never get a chance to stick around because they keep getting replaced all the time, right? So most frequently used would solve those issues, right? But it will also create a problem where if it was really being used a lot, then they get thrown out, right? So you want something with a hybrid where, so if you're going in a tight loop and you're accessing a page over and over again, MFU would keep throwing those pages out because you're using it a lot, right? And LFU would never get you started because as soon as a page is brought in, it gets kicked out, right? So you want something in the middle. So that's what happens. You intuitively something looks good, and then you try to figure out what happens when you in different scenarios. And sometimes some things go bad, and you try to fine tune them, right? And again, you need the hardware support to figure out how many times the page is accessed. If you don't have the count, you can't do any of these. Right? There are other variants, and as you notice that you are never too sure. It's never a precise science to say this page is the one which has to be replaced, because it all depends on what you're going to do in the future, right? So one way that most operating systems deal with this stuff is, rather than trying to be precise and replacing the pages only when you want them, they keep track of some pages which are always free, right? So even though, let's say your process has 20 pages, right? It always keeps 2 free, let's say, right? So when you want something, it can give this stuff to you, right? So that way, it's not being optimal in terms of leaving the pages for you to use, but it can do other stuff. So if you have to write a page back, it can write it while you're doing something else, right? So it can go through the pages and say, this page, I think it's going to be gone in a little bit, so I'm going to start writing it to the disk, right? Even though it might survive, I'm just going to optimistically start writing it to the disk, and I might optimistically throw it out of the, I might actually modify it as it's out of the page, right? So when you want a new page, I give it to you right away because I already made a decision to get some page out of the way, right? Even though you don't need it at that point. So I keep a few pages which are always free, such that when you want a new page, I always give something to you. The price I pay is I'm wasting some pages which could have been used for something else, right? And in modern systems, this tends to be better. You don't want to wait for the page fall. When page fall happens, you don't want to have a page, especially when you have bigger and bigger memory. So if you have a 2 gig laptop, then the system may decide to not allocate some pages at all, keep them in a buffer, and basically, if you want something, it gives to you, right? It assumes that it's going to be replaced. And then you can do some optimization. If you ever access that page, then it's brought back directly. So you can do these different games to make sure that when you do a page fall, you don't make a decision what to do at that point. You already have all these things decided. You pay the overhead because then now you have to write all these pages before they were wanted, right? But potentially you can give a page faster, right? And you can only do these things when memory is plentiful, right? If you only had 2 pages for your program, I can't afford to keep one of these pages hanging around for stuff like this. But if you have lots of memory, then I can do these things. Then I can kind of do these things. So in a real machine, when you modify the pages, you may see more writes than you have to. If the system is idle, it may decide to write some of the pages to the swap disk, assuming that page is going to be used for something else. And it will be put in the free buffer, assuming it's going to be used for something else. It adds to the complexity, but it gets better performance in the long run, right? And that's some of the stuff that we'll see being done in here and in the next file system. You try to use the hardware to the fullest by being wasteful, by writing stuff when you don't have to, hoping that when you do have to write it, things will be faster, right? And the next challenge is trying to figure out how much frames to give to each of the process. It's not so much of a problem anymore, but it used to be a real problem back then, right? So there is a number of frames, minimum number of frames and a maximum number of frames that each process should have. Minimum number of frames, for example, if you use the IBM 370, turns out there is one instruction which could potentially touch 6 pages, right? This was an instruction which was 6 bytes long. It's moved a chunk of memory from one area to another area, right? So depending on how these pages were set, it's potentially possible that you could be touching 6 different frames, right? Because your instruction could be in 2 different frames, part of it in one frame, part of it in another frame. The data that you're trying to move could be part in one frame, part in another frame, and so on, right? So for this instruction to proceed, you need, in the worst case, all 6 frames, right? It's not possible for you to use paging to give you less than 6 frames. Can you think of why? It's not a problem anymore because memory is plentiful, right? Suppose you have this instruction. Right? So you have this instruction which starts from here and it ends here, which is a move instruction. It moves stuff from here to it copies a set of address values from here to here, right? This is the assembly language instruction, right? So it copies, let's say, 10 bytes from here to here. Half the 10 bytes is in one frame, half is in another frame, and half is going to be here, half is going to be here. Instruction is here, instruction is here, right? What will happen if you have less than 6 frames for this process? Suppose you have only 4 frames, right? Can this instruction ever complete? So what will happen is, let's say you start, you access this instruction, you access this instruction. So they both have to be in memory. Then you try to access these 2. They both have to be filled in. Then you try to move it to here. You get a page fault, right? Then you get a page fault, and then essentially it has to replace something. So let's say it replaces this with these 2, and then it will restart the instruction. But it can't, because the instruction cannot complete because these 2 were needed, right? So you go through this phase where you can never start, because if you want to restart, you again do a page fault. So for this instruction to happen, you need all the 6 frames to be in memory. They cannot be replaced, right? So in this system, you at least need 6 frames for the system to proceed, because in this weird condition, if this happens, you can never proceed because you'll always keep getting page faults, right? So that defines the lowest one, and highest is whatever you can choose. In modern machines, you don't think about it because memory is plentiful, so you don't really worry about this stuff, right? But so it's just there because of the nature of the hardware, right? We can continue with this on the next lecture.